Welcome to Dr. Jed's Continuing Calculus video series. Today's lesson is section 5.8 from Rogowski. It has some sort of title, but what it really boils down to is exponential decay and exponential growth problems. These are probably something you've seen before, even before you had calculus, so hopefully it's kind of a review. We'll beef it up a little bit just to make it more calculus-y, but it's really still the same thing. So the first attempt at making it more calculus-like is that we're going to talk about it as the solution to an initial value problem. The initial value problem is y prime is the differential equation y prime equals ky for some number k. And the initial value is y of 0 is y sub 0. So the solution to this is simply y of t equals y0 times e to the ky. It's an exponential function. If k is positive, we call this exponential growth. And if k is negative, it's exponential decay. Sometimes we write it as y of t equals y naught e to the minus k t for decay. That way we can keep k as a positive number. It's not necessary. Some people do this with a minus k. And there is a typo here. This is actually supposed to be t. So we can do this or this for decay. In either case, the half-life for decay is going to be t equals the natural log of 2 over k. K is positive, or negative k if k is negative, the absolute value of it, basically. The doubling time for growth is going to be the same formula, because taking something and shrinking to half as fast, or half as much, is equivalent to getting twice as much later for a growth kind of problem. So let's do an example. So at time t0, we are having an exponential decay model, 400 initial milligrams of something, we'll call it calculum 120 for some reason. Which, if you really want to, we could actually have it decay into trigonometry 119, but, whatever. It's going to be an exponential decay model. The half-life is 45 seconds, so we want to write out the formula and find how much is left in 2 minutes. So the formula, we're going to need the initial amount, which is y naught, and k. But we know the half-life. Half-life is 45 seconds, and we know that's equal to the natural log of 2 over k. So that means k is the natural log of 2 over 45. Now, we can get a decimal of this. Probably want to keep 4 or 5 significant digits. Or we can leave it like this. So the formula is going to be y of t equals the initial amount, which is 400, e to the minus ln2 over 45, that's the k, times t. There's our formula. And again, you can put a decimal in here. The second half, find how much you have in 2 minutes. Well, we plug 2 minutes in. But don't plug 2 in, of course, because this is seconds. K is calculated in terms of seconds. So t has to be in seconds. So instead of 2, we'd write 120. You can multiply that out, get some value. I don't know, it's going to be some messy number, and I didn't bring a calculator. But usually you want to have a decimal answer for these kind of problems. Let's try another one, perhaps one that has a less messy answer. We'll do exponential growth. So in this case, suppose we have a bacterial colony that's growing according to the model. Here's the model. This is exponential growth. We're going to start with 1,200 bacteria. And in 2 hours, we're going to have 1,800 bacteria. So it's growing. I don't know if that's fast, slow. First of all, we want to find out the constants, the y naught and the k. Second of all, we want to find how many cells are going to be present in 4 hours. Hopefully these are relatively easy to calculate. They're not going to be super messy, but we'll find out. Y naught first. Y naught is the initial amount. There it is. Y naught is pretty easy to solve. K is less easy, but we can solve because we know how much there is in 2 hours. We know that in 2 hours, and there's no other units of time anywhere, so our implied unit of time will be hours. So y of 2, that we know is 1,800, excuse me, that's going to be 1,200, e to the negative, and we don't know what k is, but we know t is 2. We can solve by dividing by 1,200 here. we get 1.5 when we divide, equals e to the minus 2k. We can take the natural log of both sides. And when we have an exponent right here, we can pull that down. Oh, I'm sorry. I have negatives here. Why do I have negatives? Shouldn't have a negative, should I? It's growth. Okay. Growth has a positive there. So anyway, though, it doesn't change it. 2k ln e. The natural log of e, because this comes down here, natural log of e is 1. So I get 2k. So I divide, I get k is the natural log of 1.5, and then divide by 2. That's half of it. The other half is how much do we have in 4 hours? Well, we plug in y of 4. Y of 4 is going to be, just plug it in here, 1200 e to the, now that's what k is, times 4. And that's messy, but it's not really messy because we're dividing by 2 and multiplying by 2. So let's rewrite that. So it's e to the natural log of 1.5 times 2. If you remember your exponential rules, hopefully you do, e to the natural log of something is that something. And if we're multiplying by another number here, that stays in the exponent. So this is equal to 1200 1.5 squared. 1.5 squared is 2.25. When you plug that in, you're going to get 2700. Now, this is how exponential models work. But there's one thing about exponential models that's not always ideal. Exponential models grow without bounds. They grow to infinity quickly, actually. Well, they don't reach infinity, but they grow really, really, really big. If I took this model and continued it, so in 4 hours, we've more than doubled. If I waited a year, I would have more cells by mass than could fit on the planet of Earth, because it would weigh more than Earth. That's not a realistic model because the cells will compete. They'll compete for oxygen, they'll compete for food, for water, for nighttime programming on TV. Actually, probably bacteria don't do that much. But in any case, there's competition. So a better model would be one that factors in the competition. The logistic model actually has a competitive element in it. It grows initially exponentially, but eventually it caps out at a limiting factor. L is actually the limiting factor. It's the biggest this gets. So we could actually write this as L right there. Now, there's a dash here at a certain interesting spot. But before I do that, I want to point out there are 3 constants in here, L, A, and K. If you wanted to solve explicitly for all 3, you'd need 3 pieces of information, not just 2, not just an initial and a one time afterwards. We'd need initial, one time after, and then another time after that. And it would get messy. There'd be a lot of mixing and mushing. So more often we'll give you some of them, or in this example, all of them. L is 1000, K is this number, and A is that number. Can you figure out how much there is at time 0? Well, plug 0 in, get it, and you get 20. That's just a calculation. A more interesting question is, what is that point? That point is the inflection point. The inflection point is actually the maximum of the derivative. That means the slope is biggest right then. This is a great place to harvest because the population is growing as fast as possible here. It's not growing very fast here because it hasn't gotten to the oomph yet. It's not slowing down up here yet because of competition. Right in the middle, it's growing really fast, so you'll replenish really fast. If you want to harvest something, this is where you want to do it. So where is that point? Well, it's messy to find the inflection point. It's a second derivatives problem. So let's do it. So we want to find we find the first derivative here. I did it by the quotient rule. Pulled a couple pieces out. There is the first derivative. It's not very pretty. This is an important enough question, though, that doing the second derivative is valuable. So L times A times K is just constants. When you take the derivative, the constants will stay there and kind of sit by themselves. They don't change anything much, so the second derivative is going to be them times the derivative of this, which is also the quotient rule. There it is. There's lots of chains in there. And there's pieces in common. There's this term, there's that term. They each have many pieces in common. Factoring some things out, we can factor out one of these powers. There's 2, there's 1, so we can factor that one of those and one of those. Pull a k out, pull an e to the minus k out, and so forth. In fact, I even pulled a minus sign out to get all of this over here and that. Now, how does that all work? Well, inflection points are where this is going to be 0 or where it doesn't exist. Well, more precisely, they're going to be where the second derivative changes sign. But that can only occur at a 0 or non-existing. And this exists everywhere. The bottom, always positive. Everything else works great. So we just need to find where this is 0. Constant, 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 always positive, always positive. Not any of this can be 0. It's just a number. Well, it's a formula, but it's not going to ever be 0. So that has to be 0. When we simplify it, you get 1 minus a e to the minus kt is 0. That's the only way to do it. Boil this over, divide by a, take the natural log, divide by minus k, simplify. This is where the inflection point comes. So in this particular case, we could say the inflection point comes at t equals, what is it, the natural log of a, the natural log of 49, over 0.0143. Now units are important. Is this seconds? Is this hours? Is it years? That makes a big difference. But this is how you calculate. This is where you know when the best time to harvest your trees, nuts are, your fish in your pond are, your cattle, your deer, whatever you're harvesting, that's the best spot. This is how it's used. This one's messy, the other ones hopefully weren't. And until next time, this is Dr. Jet.